I study like kind of machine learning and causal inference and other topics in political methodology like text analysis and image analysis and deep learning to a lesser extent. And I also do work in bureaucracy. This is a paper that I'd really like your feedback on, and it's something that I've been thinking about for a while. So thanks for taking the time to watch this presentation. Okay, so I'd like to give you a little bit of a motivating example as to how this work had started. This is what I looked like in 2013 when I was a grad student. I was kind of like clean shaven and, probably about 40 pounds lighter or so. And, that was before I started this paper that eventually got published in Electoral Studies in 2016 called Estimating the Gender Penalty in House of Representative Elections using a Regression Discontinuity Design. And in this paper, this is actually part of my thesis. And in this paper, I used an RDD where the primary vote share was the forcing variable and the outcome was whether a man or a woman was placed on a ballot for the general congressional elections. And what I found through doing this study was that there were basically no effects. So there was no gender penalty per se for being a female candidate or having a female name on an election ballot in the general election. Now, this paper actually ended up taking 3 years to do, and by the time I finished with the publication process, I kind of looked like someone who had been sitting in a cabin for many years with a long beard, and in part that was due to the stress that was required for publishing this paper. And but I learned a lot from the process of publishing this paper. And I learned a lot about RDDs, and I learned a lot about the publication process. And so the motivation for this current paper comes out of what I learned about from what I learned about RDDs. And the one thing that I learned was that RDDs have many researcher degrees of freedom, probably more so than almost, than a lot of other types of causal inference models with observational data. Now, the comparison I'm presenting here is one in which I'm just comparing on the left-hand side. This is the case where if you just estimated a treatment effect, an average treatment effect using a regression model with a randomized treatment, right? And so your kind of researcher degrees of freedom there, the things you have to consider is, well, what's your dependent variable? Okay, what's your treatment? That's the obvious kind of thing that you have to figure out when you're talking about research design. And, if you decide to, you can also consider throwing in pre-treatment covariates. And there's some evidence that including pre-treatment covariates will improve the efficiency of your treatment effect estimates. But when it comes to regression discontinuity designs, you have those three elements, but you have a lot more, right? And I'm going to say that there's about a minimum of 9 knobs that you can turn and you could kind of play with in RDDs. And then, so in addition to those three, right, dependent variable treatment, pre-treatment covariates, then you have the forcing variable, okay? So, those are kind of fixed things, right? So those 4 are just the basic elements of RDDs. But then you have, well, like what kind of kernel are you going to use, right? And you have several kernel choices. What bandwidth will you use? Will you use an optimal bandwidth, or will you use a fixed bandwidth that's based on some substantive concerns? What method will you use to choose the bandwidth? There's the Imbin's, the IK method for bandwidth selection, and I believe there's other methods that have been coming out recently as well. Will you subset your data before you estimate the treatment effect? What type of model will you estimate? Will you have a second degree polynomial, third degree, and so on and so forth. So there's many researcher degrees of freedom when it comes to regression discontinuity designs. And so one of the problems with this is that, as researcher degrees of freedom increases, you'll tend to have more false positive results, right? So this is, hold on one second, guys. Classic working at home moment. My son just came to the door. Okay, so researcher degrees of freedom. Yeah, so you have a lot of them with RDDs, right? And you know what psychologists know very well from doing experimental studies is that the more kind of knobs and dials you have to tweak in your experiments, the higher the likelihood of getting false positive findings. And I think that makes sense, right? And in addition to that, right, you also have treatment effects that tend to be, you know, I'm going to call them underpowered, but I'm going to, you know, that might be a little bit unfair. Another possibility is to say that they're low end, right? So, you know, if this is just a brief list of very like high impact important studies in the literature, and I took the lowest number of observations that the authors had estimated a treatment effect for. And you could see that, you know, there's some studies where there's like 15 observations that people use to estimate the treatment effect. In some studies, there's like, you know, 35, and some in the higher end ones, there's like 165 and so on. But, you know, there seems to be this problem of, especially when the kind of optimal bandwidth is finally selected, of having a relatively low number of observations. And I think it's been confirmed by other folks that I've spoken with who have you know, done estimated RDDs. And I actually had that problem in my paper as well. When it was time to choose the optimal bandwidth, and I had used the IK bandwidth, my degrees of freedom were pretty small, right? Okay. And so we have this high degree of researcher degrees. We have a lot of researcher degrees of freedom. We have relatively underpowered or low end, you know, studies where these treatment effects are estimated. This kind of environment where the treatment effects are estimated in. And in addition to that, we have many different types of pretreatment covariates that people like to throw in their model. Now, this is again the same list of these studies. And so, you know, in some studies, people will throw in just only fixed effects. So, you know, in the Zacconi study, which I'm going to talk about, the author throws in year fixed effects, region fixed effects, sector fixed effects in this Russian firm data. But he also throws in time varying covariates. And in some other studies, the authors just put in some, you know, time varying covariates. And, you know, there's really no clear kind of, you know, rule or anything of the sort when it comes to adding covariates to, you know, for adjusting treatment effects in RDDs, right? And so now the problem with all of this is that the practice then of including pretreatment covariates then creates a situation in which treatment effects tend to be unstable, right? So in the small, and you know, I think everyone that's kind of intuitive to everyone. Everyone would understand that this is the case. But let me give you a little example. This is just from you know, this simulation is actually not in the paper, but you know, you can see how sensitive treatment effects are to the inclusion of covariates using this example. And I'll show you more examples with real data next, and also a little bit later on. So in here, you know, I simulated with 100 observations you know, an election forcing variable, a close election forcing variable, F, which is, you know, is a random uniform distribution between, should be negative 0.5 and 0.5. And I just also constructed two random, you know, randomly generated covariates that were weakly correlated at, you know, R equals 0.2. And I included them in the model, okay? So let's take a look at the treatment effect. This is this tau right here. That's the thing I want to point your attention to. And this is also using the kind of Kalanick, Cattaneo, and Titiunic robust measure, right? So I included that as well. So the treatment effect estimate with no covariates was 0.036, and the treatment effect with two covariates, with these two randomly generated covariates that have a moderate correlation, was 0.09. That's a very large difference, right? And we also see, of course, that the bandwidth estimated is different, and so on, right? So there's, you can see that the treatment effect itself can change quite a bit when you include covariates. But if you don't believe simulations, which I don't blame you for doing, because I don't believe a lot of them either. Let's take a look at at some real data. This is from the Zacconi paper that I'm going to talk about, which I used as the example for this particular paper. And you can see that so to give you a little bit of some brief background about what this paper is about, the outcome variable is, firm profitability, and the regression discontinuity, the treatment that Zacconi is trying to estimate is whether, a Russian CEO who wins an election, how that affects their firm's profitability. So the Russian CEO getting elected is the treatment, and then the forcing variable is the close election vote share. So the treatment effect here is basically, I forget what the exact units are, but it's some kind of, the outcome is firm profitability. So if you see this in his original paper, this treatment effect, this 0.146, this suggests that, a politician who was barely elected to office, their firm increased in profitability by, let's say, 14%, right? And so that's his treatment effect, which includes, all these covariates that I had mentioned before. But what if we kind of trim some of the covariates in a certain way? And this is the method that I'm talking about, this adaptive LASSO method, which basically only trimmed 4 covariates from the original model. We see that the treatment effect changes significantly to 0.102. And we also see that even though the standard error actually decreases quite a bit, the statistical significance, because the treatment effect point estimate dropped, that actually goes down quite a bit. That p-value increases quite a bit. Okay, so you can see that there are pretty big differences that can be that including or excluding covariates can make when we're estimating these RDDs. But should we get rid of covariates altogether? Well, I don't think necessarily we should do that, or we have to do that. There's a lot of theoretical research that's been done by CCT, and they found that the inclusion of covariates does tend to improve the efficiency of treatment effect estimates. So, well, if that's the case, then what kind of solution do we have? I mean, if we say we want to include covariates to improve the precision of treatment effects on the one hand, but on the other hand, we want to kind of prevent the situation where people might be gaming the system, or treatment effects might change too drastically when we estimate them in these kind of relatively small n contexts. So what do we do? And I think the solution that I provide in this paper is that if you do want to include covariates in your regression discontinuity design, you should include them in a way that allows for a kind of an automated model selection procedure to remove them or to exclude them according to some kind of optimization criteria, right? And that optimization criteria is basically minimizing the mean squared error of the of this model that you're estimating, right? And I got the inspiration for this from some literature in the kind of experimental context, which actually dealt more with high dimensional problems. And so one of the first papers that came out, to the best of my knowledge, although there might be other ones that came out before that, was Regularized. I'm not sure if I'm pronouncing the name correctly, et al. And that was a paper on LASSO adjustments of treatment effect estimation in randomized experiments. And so what the authors in that was actually a PNAS paper. And what the authors of that paper found is that they kind of developed a whole means of selecting covariates to estimate treatment effects in randomized experiments where there were a lot of covariates available and people really didn't know what covariates they should include or exclude. And Wager et al., I think I'm pronouncing his name correctly, there's in the same year and in PNAS as well, he also kind of did a paper on high dimensional regression adjustments in randomized experiments, where basically the idea was, well, how can we optimally adjust treatment effects through the inclusion of covariates using these automated variable selection methods like the LASSO. Okay, so at the end of the day, what these folks argue is that the best way to adjust treatment effects in randomized experiments, when you have like a kind of a lot of covariates, these high dimensional contexts, is
Hey, Jason.
yes.
I'm having a computer issue. I'm gonna have to restart my computer. I'll be back on in like 2 minutes.
Oh, okay. Okay.
Okay.
Yeah. So let's. I'm just going to keep continuing in the interest of time, but so what they argued was the way that you should apply the LASSO is to basically estimate your model and then use the LASSO as a variable selection procedure. Obviously, you're not going to use the treatment effect estimate from the LASSO itself, right? Because that's going to be biased. So you just estimate them. You estimate the whole model. You apply, the LASSO penalty, and then the LASSO basically tells you what variables to shrink, and then you re-estimate OLS and get your final treatment effect. And they have some theoretical results which show that this is a pretty reasonably stable method of minimizing or increasing precision and kind of minimizing the variance of the overall model. And of course, one thing to consider is that you want to minimizing the variance of your model, right? The kind of sigma, the overall MSE, does have effects on your the standard error of your coefficient estimates, right? So it will increase the precision of your treatment effect estimate, right? Okay, so my solution in this paper is not that creative because it kind of builds upon these other works, and the solution is basically, what if we applied the same kind of automated variable selection procedure, but to regression discontinuity designs, right? What if we just applied the LASSO to RDDs when we estimate treatment effects? What would it give us? And the argument that I make in this paper is that it can actually give us, especially in these contexts in which hold on a second, that marking. Sorry. So especially in these contexts where, let's go back here. Especially in these contexts where we have a small number of observations, as I'll show in simulations later on, we can really get the benefits of including covariates while minimizing the costs. And so I developed a procedure for incorporating the LASSO into treatment effect estimation for RDDs, and that's what I call the principled estimation method of regression discontinuity designs. And it's basically a four-step process that's based on the other papers which had adjusted treatment effects using the LASSO, excuse me, using the LASSO in this randomized experiment contexts. So in the first step, the researcher selects some pre-treatment covariates that they want to include. And these should be based on substantive concerns and can vary from model to model. Usually these might be something like fixed effects or other things like that. And if it's a closed selection variable, it might be changing demographics and things like that. In the second step, we have adaptive, what I call adaptive LASSO regularization, and that's the kind of innovation that I argue is the thing that I'm kind of bringing to the table here. And so basically from the model from step one is passed through this, what's called an adaptive LASSO. I'll explain what that is in a minute. And some covariates are selected out, right? After those covariates are selected out, then we move to step three, and the kind of final model is estimated, right? Now the covariate adjustment part here in between steps 2 and 3 is such that I keep all of the kind of core elements of the regression discontinuity design the same. So there's the forcing in the local linear regression, the forcing variable is not penalized. Obviously the treatment effect is not penalized. The only thing, if there's the interaction, if we use the difference and difference method, the interaction between the forcing variable and the treatment is not penalized. The only thing I penalized is any additional covariates defined by the researcher, right? And so then in the final estimation, the model selects out the covariates that should be removed. And finally, we do a kind of CCT robust estimation and get our covariate adjusted treatment effect at the end. So I'm going to try to go through these relatively quickly in the interest of time and explain each of these. Okay, and then I'd like to go over an applied example by Zacconi and some simulation results. And I'm going to try to breeze through a lot of these quickly. The important part is I just wanted you guys to get this the general sense of what the algorithm is here. Okay, so I think everyone pretty much knows what estimating a treatment effect for RDDs entails. So I'm going to skip this. In this paper, I basically used a local linear regression method, and the focus of this paper is pretty much on tau hat, right, and covariate adjustment of tau hat. So the covariates are this big X beta matrix, and all of the selection that the adaptive lasso is involved in is on this X beta matrix, right, the covariates that we have here. Okay, so yeah, researcher pretreatment covariate selection. I'm just going to kind of skip that. I'll move on to step 2. So let's talk about the lasso regularization. So in the initial model, you're just estimating a local linear regression, and what the model is selecting out, the adaptive lasso model is selecting out, is this subset XS of the entire covariate space, right? And so you might wonder, like, well, what is the adaptive lasso, and why would you want to use it here? Well, I'm going to talk about that in a second, right? So this adaptive lasso is basically doing the covariate selection for the final model that you're estimating with the CCT robust estimation. All right, so for those of you who aren't familiar, although most of you might be, since this is a machine learning and causal inference panel, ordinary lasso regularization involves just estimating this kind of loss function, but with a penalty term included here, where each additional variable is penalized, and there's a kind of tuning parameter lambda, which is estimated using cross validation. The adaptive lasso is a kind of a slight variation of the original lasso, and the reason I applied it in this case is because, at least according to its originator, Zhu, is that the adaptive lasso has oracle properties, and it thus tends to select out models in a way that are correct according to at least some standards. So let me talk about, I think one thing I skipped was why the ordinary lasso might be a problem in the first place. One of the problems that the ordinary lasso has is not that it doesn't do a great job of minimizing the mean squared error of a model. It does a great job doing that, but it tends to minimize the mean squared error of these linear models in a way that is somewhat random, right? So if there's a true model that you have out there that you know is the correct model, right? Lasso will not retrieve that correct model a very high proportion of the times, right? Whereas the adaptive lasso, for the adaptive lasso, that tends to be less the case, right? It has these oracle properties which allow it not only to minimize the mean squared error of the model through covariate selection, but also to select the quote unquote correct model, right? When simulations were done on the basis of some ideal model that was proposed originally. And this kind of makes it a very stable lasso method for selecting covariates in cases where, again, you don't want the treatment effect to change drastically when you select covariates, when you're kind of selecting covariates out, right? And it also, because it involves just the placement of a weight parameter in the lasso penalty, it's easy for you to incorporate some zeroed out weights for RDDs. But really, it's really the oracle property that that kind of made me think about the adaptive lasso as opposed to the regular one for this context. And I could talk about this about the adaptive lasso a little bit later if you'd like, but this is basically, so like here's the original lasso, that's the penalty, right? The L1 penalty. And the adaptive lasso also has an L1 penalty, but now we have this kind of omega weight. And the omega weight is just basically 1 over the absolute value of the parameter to some power, right? And this parameter, this is another kind of tuning parameter that's estimated via cross validation, the gamma. Okay, so you apply. So we're on step 3, right? So you apply this adaptive lasso method, and I kind of developed a whole R package to implement this. And some covariates are shrunk, and some are not. Again, the way it's designed is so that none of the quote unquote main effects of the model are shrunk. Those are all kind of, they're not penalized at all. And the final model is the kind of modified covariate set. I call this X naught here. And so, then you have some options as to what, how you want to choose bandwidth, right? So once you've selected those covariates out, you can either estimate your final treatment effect using an optimal bandwidth, which is what most people will tend to do, or using a fixed bandwidth, which tends to be done in the small, in the kind of not the small n RDDs, but the close election RDDs, where people sometimes the optimal bandwidth will be way too far away from the cut point, like 10% or something. So there's, if I remember correctly, there was a kind of rule that was published that you should estimate at least, you should at least estimate some kind of 5% window around the cut point when you have these close election RDDs. And I'm trying to remember exactly where that paper came from, but I see this rule being applied in many of the papers that I've seen while doing this research. Okay. And then finally, it's just, everything is just normal after the covariates are selected out, and you just do CCT robust estimation, right? Where you're basically just estimating the treatment effect with the covariates that had been selected out by the adaptive lasso model. All right, so let's just go through quickly an applied example where the adaptive lasso was, or this principled method was applied in through a replication of a paper published in the American Political Science Review by Zacconi in 2018. So Zacconi, his paper is part of a very interesting literature which uses close election RDDs to explore what the returns to office are in Russian firms, right? And so, or I'm sorry, in Russian government. So as I mentioned before, his outcome is firm profitability of a group of firms, and in Russia, and his treatment is whether the kind of board members of those firms were elected to office or not, and the forcing variable is basically vote share for these elections. And so what he finds, and this is not my plot, this is actually taken from Zacconi, is that there tends to be a relatively large increase, at least at this, when we look at the local average treatment effect here around this margin of victory in firm profitability as a result of being elected to office. Now, an interesting thing that someone else had pointed out when I presented this last time was, why does profitability drop so much when these individuals barely lose the election? And I don't really have a good explanation as to why that is. You'd have to ask the author. What's that?
They were hoping to win.
Yeah, apparently. Exactly. Maybe they spend too much money on their on the campaign or something. That could be too much of their company's money.
Or their opponents won the election and then crushes them.
Oh, then crush them. Yeah, there you go. Man, that's a great point, actually. Okay, so here's the Zacconi estimates a couple of models in this paper, but here's the general form of the models that he estimates. I mean, when I say a couple of models, I mean he uses one or two different dependent variables, but the general form is as follows, right? He's most concerned with this district win, so that's his treatment effect of being elected for these officials, and then he has he uses kind of typical diff and diff local linear regression with the vote margin and the interaction between the district win and the vote margin as like, you can call this like your main effects or whatever, and then the covariates he includes are a group of fixed effects. Those are represented by Y, S, and R here, and some time varying like candidate and district demographics, right? And I forget exactly what the districts were. They were I don't know that much about Russian geography, but there were several levels of geography that were included as controls in this model. All right, so let's take a look at the treatment effects and how they change when this procedure is applied. Now remember, I didn't do anything to this, okay, except for literally just use a LASSO method to select out covariates, right? That's all I did, okay? In the original, this is one regression that was done, is we have the treatment effect was 0.146, is what I had talked about before. And when 4 covariates are removed, which were shrunk to 0 by the adaptive LASSO methodology, this kind of our treatment effects shrinks to 0.102, and the standard error also decreases. Okay, so these two results. The first two are where the IK bandwidth was used to estimate the treatment effect. He also does another set of analyses where he chooses a fixed bandwidth. That's the 5% bandwidth, and those are the other two columns, the original 5% APSR and the adaptive 5% models, right? So this is where like we instead of using the IK bandwidth, I forget. So the bandwidth here you can see is pretty like high. Okay, it's 11%. That's a pretty big bandwidth in this case, right? So that's why he chooses this 5% bandwidth to just check the robustness of his results. And in the 5% bandwidth case, his treatment effect increases. So originally it's 0.146, and after that it's 0.198. And I still find that the effects are statistically significant after applying the adaptive LASSO procedure. But there's a huge, I mean, like the procedure only removed 2 covariates, 2, right? And there's a significant number of observations. It's not like it's tiny, it's 201 observations. And through only the removal of those 2 covariates, we see a drastic decrease in the size of the treatment effect. Yeah.
What were the 2 variables?
That's a good question. I should actually find that out. I think I had meant to figure that out, but it just kind of slipped my mind. But I will try to figure that out because I'm very curious to know what they are as well. Okay. So, all right. So okay. So that's the applied example. Again, you can see that there are some nice things that come out of using the LASSO to select out covariates. We do get it is clear that we do get these kind of smaller standard errors at the very least, right? Okay. So let's talk about some simulation results. Now, of course, if you're going to apply a method like this, you want it to improve the precision of the treatment effect, and I mean it should theoretically, but when it comes to small n context, there's a lot of randomness that might occur, and that's why I wanted to demonstrate that this method would actually work using simulations. And also the adaptive LASSO it's kind of a method that has not been used that frequently in the literature, to the best of my knowledge, even since its publication and since the publication of that original paper in 2006 by Zhu. So I did a series of what I call realistic simulations, and I'm happy to talk about them after the talk, but basically these simulations had were based on real parameter estimates. So imagine taking real means and variances for a real data set. I actually took it from Zacconi's data set, and then generating simulated data sets on the basis of those parameters alone, assuming that each variable is comes from a standard normal distribution, right? Well, each one that should come from a standard normal distribution. Some come from a uniform distribution, the way that these simulations worked is that this is the true model, right? That should be captured. And so the outcome variable, right, the simulated, this would be like a simulated firm profitability variable, YS, is equal to, 0.3 times the simulated district win. So 0.3 is the, is the true treatment effect. And, all we have here is like the typical diff and diff model. So there's like no covariates. In other words, covariates should not be included in this model, okay, in the true model. And I compare, so this is the true model, right? And the true treatment effect is 0.3. And then, but the estimated model is the same kind of, true model here, but with some covariates that are included that are based on, using some realistic assumptions about what those covariates should look like. And I do these, so this first set of simulations is based on an n equals 500 sample, and I do 2,000 of those simulations. And so let's kind of see what that looks like. So there's the two performance measures that I look at are percent coverage and bias, right? Of the treatment effect. So how far away on average for each simulation is the estimated model away from the the true model. And so this is the distribution of the simulated treatment effects for the adaptive LASSO model. That's this model with this peak here in gold versus the conventional. And as you can see, the estimates are, because the adaptive LASSO model basically selects out those extraneous covariates. These estimates kind of bunch more closely towards 0.3, the true treatment effect, than when we include the covariates without any selection. Okay, and let's look at some of the other numbers, and just these are just averages, and I kind of explore this using both the variable bandwidth approach and the fixed bandwidth approach, and you can see that when there's variable bandwidth, so basically we just let the IKA procedure select the optimal bandwidth. We find that the adaptive LASSO, the bias is 0.27, and under the conventional method, the bias is 0.397. So that's a statistically significant difference there, right? When we let the kind of IK algorithm choose a bandwidth. Percent coverage, I think the results are much more dramatic, not surprisingly, because the point is to improve precision, right? So percent coverage is about 95%, which is what we would expect for the adaptive method. And for the conventional method, when we include these extraneous covariates, it is 70%. And that difference is also statistically significant. Okay, what about when we fix the bandwidth? So when I say fixed bandwidth, I mean like constrain it to 5%, and we do the same, we do the same simulations. Well, in that case, when at least for this simulation in particular, when the bandwidth is fixed, there's not really too much difference in terms of bias. So the adaptive method and the conventional method returns the same, roughly the same average bias. However, once again, in terms of coverage, which is, again, that's the whole point of this, is to improve the precision of the treatment effect estimate, so it makes sense in many ways that coverage will be better. In terms of percent coverage, we see that adaptive recovers the roughly what we would expect for the percent coverage, and conventional does significantly worse. Okay, so now that's with this, n equals 5. This is like a set of simulations set to n equals 500. What if we do some simulations where we vary the number of observations under this using the same models, and look at percent coverage and bias for small lower n RDDs to higher n, or to asymptotically higher in RDDs. What do we get there? So each of these points here, so on the x-axis here, this is the number of observations, and for each observation, I think the observations were done in batches of 5, right? So there was 80 observations, and then there were 1,000 simulations done with 80 observations, 1,000 done with 85, 1,000 done with 90, 95, and so on. And the average percent coverage for each n is basically documented here. And so you can see that the coverage, when the number of observations is relatively low, a percent coverage for the kind of standard method when we include these additional covariates is much, much worse. And it does get better as the number of observations increases, and they almost kind of converge as we go to 400 and so on. But you can see that the adaptive method still tends to do better and is significantly more stable across all low end to high, from like 80 to 400 observations. And we see a similar pattern with bias, but with bias, this basically average bias again over these simulations for each n. The average bias is lower for the adaptive method when we apply the adaptive method in the lower end context, but they both kind of converge to roughly the same value, roughly the same value as we go past, say, 200 observations or so. You can see this in the line. They basically kind of become the same. Okay, so conclusions. I think including covariates is good, and in the case of RDDs, and it's a practice that should be done. There are certainly theoretical results to back that up, but it can be problematic for low-powered or underpowered designs. And this method provides a way to, include covariates in a way that is that allows the kind of treatment effect to remain relatively stable, and to retrieve a kind of optimal treatment effect, or at least to basically achieve an optimal or estimate an optimal treatment effect that is, has the highest precision possible, which is pretty much what you want to do when you include covariates anyway, right? So the way I like to frame it is that this is a kind of method which kind of minimizes some of the drawbacks at the end of the day